So, welcome to problem solving session for computational commutative algebra. Today we will discuss problems related to syllabus from week 12, that is computing CGGs, Koszul complexes, Koszul regularity. And I am Siddhi Balu Ambore from IIT Gandhi. So, let us start with the first question. Question 1. It is true or false. So, let R be, just a second. Yeah. So, let R be kx1 to xn, and we consider this I contained in this ideal x1 up to xn square as an R ideal. Okay, so this R is a polynomial ring in n variable, and this I is the ideal contained in this ideal generated by variables square. Okay, so this ideal here contains actually all the elements of the form xi square and xi comma xj, sorry, xi into xj, I not equal to j. Okay, so this is the ideal x1 up to, it is generated by these kind of elements, and this I is inside this ideal generated by these 2-degree monomials. Okay, so if they have given this condition that in G Rayleigh of I colon R xi is equal to G Rayleigh of I colon xi for every I, then this I is not a prime ideal. Okay, so we have to check whether this is true or false. Okay, so this is the condition given that I is contained in x1 up to xn, so ideal generated by this x1 up to xn square. Okay, so first thing which we need to check here is that no variable belong to this ideal I. So note that xi doesn't belong to I for all I, because since I is contained in this ideal generated by x1 to xn square, and clearly this xi doesn't belong to x1 to xn square. Okay, so therefore we have that xi is not in I for all I. This is true for every variable x1 up to xn. So this was the first thing which we needed to observe in this case. And second thing is we have to check whether I is prime or not. Okay, so what will happen if I is prime? And given condition is in terms of I colon xi and this initial ideal of I colon xi. Okay, so if I is a prime ideal, then I colon xi is I. Please observe this, because since if any alpha belong to this, so clearly for any given ideal, this I will always be contained in, so I is always contained in I colon xi. Okay, this is true for any variable. Instead of xi here, if I had any element from ring R, this condition still holds, that I is always contained in I colon some alpha, whatever that alpha could be. Okay, so this is there, and So if I have some alpha belongs to I colon xi, so this imply that alpha into xi belong to I. Okay, but this imply either alpha belong to I or xi belong to I. Okay, but note that xi can't be in I. Okay, because if xi belongs to I, then this I colon xi will be whole ring R, which is given to be I. But prime ideal are never the whole ring. I mean, we do not have that notion that prime ideals are always need to be a proper ideal. So that's why we have this that xi is I mean xi can't be in I. So therefore my alpha must be inside this I. Okay. So this implies that this I colon xi is contained in I, and therefore we get that I is I colon xi. Okay. So this was the thing which we had to observe. So now we have this facts. You can check this also. I mean, it's not difficult based on the definition of uh, monomial ideals and how we define GCDs in polynomial rings and so on. So the fact is that if I is a monomial ideal, and if V is some, okay, so let me write it. V is a monomial. Uh, V is a monomial anywhere. I mean, V could be monomial. So let us have this I inside R. Then V is a monomial in R. And let Gi. So if you remember, this Gi be the generating set of I. Okay, so this Gi is actually when we start, we consider it to be a minimal generating set. Okay, minimal, when we say for a monomial ideal, the minimality holds with respect to uh, inclusion as well as divisibility. Okay, so this Gi is that generating set of I, and then this G by GCD of G comma V such that this G belongs to this generating set of I is, I mean, this set forms the generating set of I colon V. So I was my monomial ideal, and V is any monomial in R. So if I want to find the generating set of this I colon V, then this set here, will highlight it. This set here actually gives that generating set of I colon V. Okay. So this happens only in case of monomial ideals. So, oh, okay. And you can check this. It's not difficult to verify. And so we have this condition that I colon V, because we need to work with this I colon xi kind of thing, where this xi is a variable, but we can consider it as a monomial in my ring R. So okay, uh, so now consider, suppose if I is generated by this F1 to Fr, uh, with the Grosvenor basis, again F1 to Fr. Okay, so if I consider this I generating set F1 to Fr, and I consider that this I I mean this F1 to FR also form the Grosvenor basis of I. Okay, and this, so if I is generated by F1 to FR and this F1 to FR is also a Grosvenor basis of this ideal I, then this initial ideal of I will be all this initial, it will be generated by all these initial terms of F1 to FR. Okay, that's the, what we say, that's the observation, or that's a property we have for Grosvenor basis. Okay, so if I is generated by F1 to FR and F1 to FR are also Grosvenor basis of I, then the initial ideal is generated by this I and F1 to up to I and FR. Okay, so, and this also, I mean, the when we consider Grosvenor basis, the minimal Grosvenor basis, this IN, this ideal is minimally generated by this F1 to FR, and then by this above fact, we can say that the generating set, then by, okay, then by above fact, generating set of, generating set of what? I, this initial ideal I colon xi, okay? Initial I colon xi is this set. Initial of fi, that is g divided by gcd. Again, initial fi, I mean leading term of fi, comma xi. Oops, not fi, f1, comma, so on up to, again leading term or initial term or highest degree with respect to the given order term is this fr, comma xi. Okay, so this we denote by 1, let us say. So I hope this so far is clear. What we want to do is that if this is a given condition, that initial ideal with respect to this graded reverse lexicographic ideal, I mean this is the given condition, and we have to check if I inside this ideal x1 up to xn square, if this satisfies this condition, this highlighted condition, then we have to check whether this I is a prime or not. So we have made this many observations so far, that no variable belong to I. Second thing is that if I is a prime ideal, then we have this. Okay, and this is true for any. So instead of this xi, we can choose any a belong to my ring R, and this still holds if I is a prime ideal. Okay, and next we have this fact that if I is a monomial ideal, V is any monomial in R, then I colon V has this generating set here. This, I mean this generating set. Okay. And second thing, so if we start with the Grosvenor basis of I, then this initial ideal will be generated by this initial terms of F1 to FR. And in that case, this ideal will be generated by these terms using this fact. Okay, so we are here so far. So, but it is given that initial ideal of I colon xi is equal to initial ideal of I colon xi for all I. So this is different thing. Okay, so here I have initial ideal of I, then I am taking colon of this ideal with respect to xi, and here what I have I colon xi, then I am taking initial ideal of that ideal. Okay, so if, so anyway, if I was a prime, if I is a prime ideal, then I colon xi is I. Let me write suppose. Okay, so this will imply what? This initial ideal of I colon xi will be initial ideal of I. Okay, this for all I. This is my second fact. Is this okay? Because see here initial ideal, if I colon xi is I, then initial ideal of I will be this I colon xi. Okay, sorry. Initial ideal of I. But initial ideal of I is equal to initial ideal of I colon xi. So we get this. Is this okay? I mean, we are just substituting this here. So what I had here, so here I'm just substituting this I again, and I get initial ideal of I colon xi is equal to initial ideal of I. From this. Just substitute or from this. Okay, or let me just name it. If I call this, then from 2. Is this okay? Just I am substituting this I colon I to be I here, and I get this similar. The 2 becomes this statement here. Since this F1 to FR is a Grosvenor basis. Okay, so this implies this I and F1. I mean, again, this is the fact we know. FR is a generating set of I. Generating set of this initial ideal of I. Okay, and we already have from here that this, and we have this initial ideal of F1 by GCD of initial ideal of, sorry, not initial ideal, leading term of F1 comma xi up to initial term of FR divided by GCD of initial term of FR comma xi is generating set of this I, initial ideal of I colon xi, which is nothing but this initial ideal of I, right? But both these are minimal generating sets, okay? I mean, this one for sure is minimal generating set, and this one will also be minimal generating set because both of this set has cardinality R. Okay, so this, and here F1 divided by this term initial ideal, I mean GCD of this thing. So since both of these are minimal generating set of this monomial ideal I, so and minimal monomial generating set of any given monomial ideal is always unique. Okay, so these imply, so these are minimal generating sets. So this imply what? If I compare them, then this initial of, let me call it Fj divided by GCD of, this will be equal to this initial term of Fj. Okay, is this okay? So we are just comparing each term. So, and then this will give me that GCD of in Fj comma xi. This is for all 1 less than equal to j less than equal to r, and for all 1 less than equal to I less than equal to 1. So this will give me this GCD of in Fj comma xi is always 1. So what does this imply? That no variable is available in the initial term of my uh, my generating set fi. So I mean no monomial xi does not So this implies that does not divide, xi does not divide for all j and for all I. So this implies that initial term of fj for all j will be some constant k. So which is not true because the monomial orders which we have, one is less than all the other monomials. Okay, so if initial term of something is one, then that polynomial becomes the one itself. Okay, and so this imply my ideal I to be the whole ring. Okay, so this is actually contradiction because we started with the proper ideal and it turns out that contradiction as this imply I is holding R, but I we started with the prime ideal. So therefore I is not a prime ideal. Okay, and if you don't even want to do this, then I becomes R, and this imply that and in that case, which is not contained in x1 to xr square. I mean, anything you have to assume. This will happen. Okay, because, or forget about this. You can just say that because I is contained in x1 to xr square, xn square, and we have you proved this fact that in I think second or third lecture of this live section, live sessions, that if I is the ideal which is inside this ideal, the same ideal, this which we started with, then Grosvenor basis, all the elements of the Grosvenor basis of this ideal will have degree greater than equal to 3. Okay. Sorry, degree greater than equal to 2. And in that case, none of the xi is dividing this fj. So um, it contradicts to that result which we proved earlier. Okay. So when I will upload the notes, I will maybe try to write which lecture number was in which we proved or observed this. So that's why I is not a prime ideal. Okay, so this is a contradiction. So this statement here is actually false. This statement is not true. Okay, because we all saw these facts everywhere, and we arrived at the conclusion that xi no variable divides the initial term of fj, but this fj is ideal in this ideal generated by variable square. So, and the Grosvenor basis must have degree at least greater than equal to 2 in that case. So, that's why this I is not a prime ideal. Any doubts here? Please let me know if you have any doubts. If you not, then I will move to the next question. Otherwise, you can write the doubt in the chat if there is any. Okay, let us move to next question now. Again, this is also a true or false statement. Okay, so let R comma M be a Noetherian local ring, and this x1 to xn are just some elements from this maximal ideal. Okay, so it is local ring. It has only the unique maximal ideal, and this x1 to xn, I'm assuming these are the elements from this maximal ideal M. Then the statement is that then the Koszul complex. I will define what Koszul complex is. On this x1 to xn is free resolution. We saw what free resolution is in the last lecture. I will still try to recall it. So what they are saying is that Koszul complex is also complex. So what they are saying is, if I choose any n elements from this maximal ideal M, then whatever the Koszul complex for those n elements we have will give us the free resolution of this quotient ring R quotiented by x1 to xn. So this is the question, whether this is true or false. That's what we need to check here. So regular sequence, let me just, not regular sequence, sorry. Koszul complex, yeah. The Koszul complex, what is it? So let us define Koszul complex. So to define Koszul complex, we first need to know what is mapping cone. So what is mapping cone? So let this f dot comma small f dot and g dot comma small g dot be complexes of R modules. So what does this imply? That this capital Fi are these free modules, and Gi are the small f and small g denote the maps. Okay, and these are all complexes. So let me just write what does this imply. This f naught comma fi is this f2 going to small f2. Now this is a map. Let me write it above. This small f1, f0, and second one is this. So this is what it is. Not I, f dot, g dot. Okay, and here also it is g2. Again this map g2, g1, g0, and 0. Okay, I have this map here. And since these are complexes, so these imply with condition that fi of fi plus 1 is 0, yes, and gi of gi plus 1 not is 0. So we have these two conditions. So this is the complex. These are two complexes which have. So for these complexes, we can define a map of complexes alpha dot from this f dot to g dot, and is a family of maps alpha I from fi to gi. So these are these maps fi to gi. Okay, we have such maps here. But this map satisfy such that for all I, this the following diagram commutes. What is the diagram? So it is mapped between these things, right? So fi is, so these are my alpha i's here. This is alpha 1, this is alpha 2, this is alpha 0 maybe, yeah. Such that this diagram commutes. fi to fi minus 1, and here I have gi to gi minus 1, and this is my alpha I minus 1, this is my alpha I. This diagram commutes. Okay, and what does this diagram commute mean? Okay, this diagram commutes, and what does this imply? That this, here it is fi, here it is gi. So this alpha I minus 1 composed with fi is equal to, so this map here from here to here, and this map from here to here, they must coincide. So this is equal to gi alpha I. Okay, so it is collection of all these maps alpha i's. So I had these two complexes, and between these two complexes I have map of complexes, this which is denoted by this alpha dot. So when we say, so using these two information, we try to create a new complex altogether. And how we define, how we construct that. So given alpha naught from f dot, f alpha dot from f dot to g dot, we construct this c dot comma delta dot. Again, this delta dot is collection of it. It has to be mapped from ci to ci minus 1. Okay. So as follows. So how we define this? That c0 is g0 here. Remember this diagram. And c1 is g1 plus f1. I mean, this construction is already there in the lecture. You can check that. And in general, it is gn composed with fn minus 1. Okay, so how this map is, so I have these complexes, and how this delta I map is defined. So delta I from ci to ci minus 1 is defined like this, gi 0. So these are all free modules. Okay, so I have this kind of, and these are direct sums here. So I'm just looking at them as a block. Fi minus 1, alpha I minus 1. Okay, so this is how this map is defined here. So this, I will just give, so then the Koszul complex is, so for F1 to Fr in R, Koszul complex of Fi is just this, R going to F1, R going to 0. That's it. That's the only map that, I mean, this is how we define a Koszul complex for one element. And in general, for K F1 to Fr, it is mapping cone of the map of complexes, where this K dot F1 to Fr is just multiplication by F1 to Fr minus 1 here. So this alpha I, which we had earlier, are replaced by just multiplication by next element. So for how this works is a quick example here. So what we do is we start with this f naught. So again, they both are same actually. So if f naught is my 0 going to r, this is multiplication by f1. And similarly, it is the same element, same, what I can say, complex here, multiply by f1. And this alpha is multiplication of fr. So for fr minus 1, the multiplication was by fir. So it is f2. Here also it is f2. And we can see that the composition works here. Okay, and how then this my Koszul complex of f1 comma f2 will be? This is first c0 is what? G0. So this is my G here actually. So this is G0, which is R. And again, FC1 was G1 F0. So G1 is this, F1 is this. So this is R plus R. And C2 is again this is 0 and this is R only. So it becomes only R here. Okay, so this is my at least the map modules of Koszul complex. And then how the map is defined? Like this, Gi alpha I F minus Fi minus 1. Okay, so this is kind of, this is 2 copies going to 1 copy. So the map will be, what I can say, the matrix will be 1 cross 2 matrix, right? So 1 cross 2, it is Gi alpha I minus 1. Gi is this, which is F1, alpha I minus 1. So it is F1. So it is F, which is F2. Okay, it is multiplication by these elements. And similarly for here, it will be 2 cross 1 matrix. Okay. And here what it is? Alpha I minus 1 minus Fi minus 1. So alpha I minus 1 is F2 minus F1. Okay, so that's how these maps are defined. Okay. Is this okay here? And this first one is G1, that is 0. So yeah, yes, this G1 map, which was supposed to be here, Gi, that is actually 0 in this case. So that is okay, but I hope this, how the Koszul complex is obtained is clear. So what we have to give is, so we have to check whether this is true or false. So that's how the Koszul complex is obtained. And we have to check whether if x1 to xn are any element of F. So that's how we do it. This x1 to xn, we start with this single Koszul complex, then map them. Then again, I have two complexes of F1, F2. Then I will do this k F1, comma F2, and again create a map here. And now the Koszul complex of those two maps. These two complexes, k dot F1, F2. So that's how we do. It's kind of recursion in which we create the Koszul complexes. But we have to check whether in Noetherian local ring, whether a Koszul complex for elements chosen from the maximal ideal gives the free resolution of that of those elements or not. Okay, but for that we have this result that for Noetherian local ring, the let x1 to xn belongs to this maximal ideal M, then this Koszul complex f1 to fr, oh no, sorry, not f1 to f1, x1 to xn is a free resolution of this r x1 to xn, which is what is asked in the question, if and only if this x1 to xn is a regular sequence in R. Okay, it has to be in R. So this is the condition that a Koszul complex will be free resolution only if the x1 to xn forms a regular sequence or not. So if we want to say that this given question, that in a Noetherian local ring, if I start with the Koszul complex, uh, it will be free resolution, then my x1 to xn has to be a regular sequence. So can we find a regular a Noetherian local ring where we cannot have a regular sequence in it? The example of non-regular sequence in a Noetherian local ring. That's what we want. Because choosing, this choice of element x1 to xn need not always form a regular sequence. Okay, and that's what we will do here, that we want a Noetherian local ring. So this is Noetherian ring, and this is Noetherian local ring, and with maximal ideal x. Okay, and let x bar belongs to this M. Then this x bar is not a regular sequence, right? Because x bar is a zero divisor in my R, in R. Therefore, x bar belongs to M is not a regular sequence. Therefore, by this fact here, or let me write here fact or theorem, whatever. Therefore, this what I wanted to say, that therefore Koszul complex of X bar is not a pre-resolution of R mod, R mod X bar. Okay, so this is clear. All we wanted to do was to find a non-regular sequence in an Eulerian local ring. Because here, when the question is asked, there is no condition imposed on x1 to xn apart from the fact that they belong to this maximal ideal. So in short, x1 to xn are any, so since we are in local ring, they are just some some they are some non-unit elements. I hope that is okay. And also the definition of Koszul complex, I hope it is okay. If not, please let me know. And also, we can obtain the Koszul complex of ideals in Macaulay too. So let me just try and share the screen. Okay, good. So we will just see how it is calculated. Just a second. In Macaulay too. I hope the screen is visible. So let me zoom it a bit. So to find Koszul complex, we need this package in Macaulay too. So in general, so there are many packages in Macaulay too which help us. Which we need to call for accessing certain functions available in Macaulay too. So to find Koszul complex, we need to use this package, chain complex extras. Okay, let me just again call it. Needs Okay, so the package is load. The package has been loaded now, and now we will just find. So whatever ring we chose here, what was it? It is R is equal to QQ T quotiented by this ideal T square. This is my local ring which I started. Okay, and my I is just this ideal. Oh, okay. I think I wrote X, but let it be. T is also not a problem, just a variable. Here I is ideal T, which was my X. Okay, and I need to find Koszul complex. So let K be Koszul complex of this ideal I. So it is showing me this. It is just one element. So even in our Koszul complex, the way it is defined, it is just one element. R going to R multiplication by that Fi. That was my Koszul complex, and that's what is given here in Macaulay 2 as well. But if I find a resolution of this ideal I, okay, so if I let R be not R, not small r, let us call it C. C be resolution of I, then it is this R1, R1, R1. We need at least a complex of size 2 to find the resolution of this ideal I. So definitely these two are not equal. Okay, so even that was what asked in the question, that Koszul complex is not equal to the free resolution. So when we give this command resi, it gives a free resolution of my given ideal I. Okay, and you can check this for other Noetherian local rings as well. So for example, we can also do this. Let But this is clear for now, right? That the Koszul complex is not equal to free resolution of this R quotiented by. So yeah, let me just write this as well. Check this as well, that resolution of R mod I. Oops, sorry. What is I mean, the resolution of ideal I and resolution of R quotiented by I is the same thing in Macaulay too. Okay, so that's not a problem. But yeah, resolution of ideal is that's what we are calculating here. But apart from that, let us try this. R is equal to QQ x comma y. Sorry, I'm taking this now quotiented by this ideal x square comma y square. This is also again a Noetherian local ring. And in this case, again, if I calculate the Koszul complex of ideal X is this. Again, for a single element, it is always the case. And if I calculate this resolution for this ideal, it shows me this. It requires the chain of 3 elements to find the resolution in this case. Okay, and we can also even check for ideal generated by x comma y, and here for ideal generated by x comma y as well. And it is different. It is completely different. Even the maps are different in this case. From this, in the second fi. So for example, fki delta I here and here, the resolution needed at second place is completely different. I mean, I hope this is clear. That resolution, I mean, the Koszul complex did not give the free resolution for a given sequence of elements and ideal. Okay, so I hope this much is clear. If you have any doubt, please let me know. Otherwise, I will go back to the question. Okay, so I hope. Okay, great. So we'll move to the next question now. Question. Let me just check that question first. Week 11, question 9. Yeah. Minimal representation of this. So you want me to, okay, so let me write the question and we will check the minimal presentation in Macaulay 2 itself. Okay, so let me just write this question. So question 3 is this question. Just a second. Yeah. It is, let assignment 11, question 9. Okay, and it is what? R is, let R be K, U, V, X, comma, Y. And I is, this is the correct question, right? This is the question you are asking. Yeah, I think, yeah. Please let me know if this is not the question. So ux comma uy, yeah, ux comma uy, vx comma vy, then a minimal presentation of for I is this matrix minus u, like minus v u 0 0 0 0 minus vu minus y 0 x 0 0 minus y 0 x. And we have to check whether this statement is true or false. So we will directly do this in Macaulay too. Just a second. Let me share the screen again. And we have to check the minimal free resolution. Sorry, the minimal presentation of this matrix. So again, we will clear everything. And what is the question? Yeah, R is U V X Y, and we have to find a minimal presentation. So let M be the matrix. I mean, we know there are multiple ways to find minimal minimal representation or minimal presentation of any matrix. It is U star X, U star Y, V star X, and V star Y. And N is image of this matrix. And now presentation N. Okay. It is just shuffling of the given matrix, given elements, right? Or is it not? So what first row here is minus y. Wait. Ux, uy, vx, vy, and ux, uy, vx, vy. Or let me just, it will be same, right? So what is the problem here? Minus y into x is this. And what is the problem here? If I take minus y. So here the elements are here correct, right? Minus y into first element. It is minus uyx plus this x uy is 0. So these are correct definitely in Macaulay too. In question, okay, it's not correct, right? The first row is in the question it is minus u minus vu. So minus vux is minus vux plus u square y. So this must be false then in this case. Yes, it's not correct. Even the second column, let us check. Or second column is minus v square minus uy. And if I take transpose of this, okay, you are saying something? Yes, yes, okay, I understand. Okay. Yes, yes, that's what I'm checking. Even if I take it horizontally, uvx, yeah, it's false actually. It's not true. Okay, so maybe I will email this in the discussion forum for this question. Okay, but in the presentation matrix, it's definitely correct. And even if we don't go for the minimal representation in the Macaulay 2, from the matrix which is given in the question itself, we can see that it's not giving us the zeros of that CGG of that ideal I or the kernel of the map which we need. Okay. So let us put this in the discussion forum and let's see what we get the response. Uh, but yes, I mean, it appears to be a false from the Macaulay 2 and even by looking at the equations which we can get in CGG. Okay, so let's get back to the question here. Okay. Yeah. Mm, let's stop sharing this. Yeah. So this is actually false. Let us write this. This is false because from the first row itself, no. It will be, let us check this. This matrix into ux, uy, vx, vy. It is minus uvx. And here third term becomes minus vxy. Even this is wrong. And if I take it like this, ux, uy, vx, vy. And here minus uvx minus u square plus u square y. So both of them are non-zero. So this is not a minimal presentation. So not a minimal presentation for I. Yes. So any more, I mean, any other question? If not, let us then move to this next question. Yeah. The next question is also related to what we say. Let, what is, okay. Question related to graded Betti numbers. So if if we okay, let us discuss that question now itself. question related to graded Betti number. Or we have one extra session tomorrow as well. So can we do that tomorrow? And today we will discuss the problems related to week 11, so that those who want to watch this video related to syllabus from week 11, we can finish this. And if we get a time at the end of today's lecture, we will definitely go for Betti numbers. But we will discuss this Betti number question definitely in tomorrow's lecture. Okay. So for now, let us move to this. I mean, I have the, what I can say, not solution, but we can discuss the Betti numbers, but let us see how far we go for this lecture. So question 4. So let us check for question 4. So let R be this x comma y localized at this prime ideal xy. Okay. And this ideal I is x square comma xy R. Then there exists A belongs to R mod I such that Koszul complex on A, this element A here, this A and this A are here, is exact. Okay, so we have to check this. So there exists A in R such that Koszul complex on A is exact. So what does this imply? So Koszul complex is exact means, so Koszul complex on a single element is just this map by multiplication by A. That's what, oops, not here, it's I. That's what we saw. So K of A is what? It is just R going to R multiplication by A. Okay. And if I want to say this, if I want to say that this is exact, it means what? I want to check whether this map is injective or not. That is, this A is a zero divisor in my ring R mod I or not. So this is actually true or false. Okay, and we have to check whether this, when does this Koszul complex becomes exact? And the answer is false here, because what exactly we will show that every non-zero non-unit of R mod I is a zero divisor. Because multiplying by unit, I mean, that won't help us anyway. So we have to check that every non-zero non-unit needs to be what I say, a zero divisor of R mod I. So what we have, this R mod I is isomorphic to what? It is isomorphic to K xy quotiented by x square comma xy localized at this ideal x comma y. Okay. So then x square comma xy is x square comma x intersection x square comma y, and this is just ideal generated by x intersection x square comma y, right? Since we are in monomial ideals. So associated primes of this k xy quotiented by x square comma xy, and consider the localization as well. It doesn't matter, but yeah, x comma y. So, and we know then the zero Yeah. The zero divisor of R mod I in this case will be what? These two union of P belong to. Okay, so this is what we know. It is union of all the associated primes, the zero divisor. So in that case, this is just x comma y r. Okay, so zero divisors, and since this is local, it is localized at x comma y. So this localization gives us that every non-zero non-unit is anyway inside this ideal generated by x comma y. Okay, but any non-zero non-unit is exactly, I mean, it is exactly equal to this ideal x comma y, and we have proved this. So, so no such A exists in R mod I such that the Koszul complex will be exact. Okay, so is that clear? If A actually needs to be non-unit, we have to start with the non-unit here. Because multiplication by unit won't actually give anything as such, but yeah. This A is just an element. So yeah, I mean, we are talking about complexes, and so I hope this is clear that every non-zero non-unit in this ring is this ideal generated by xy, and that's why no element exists for which this Koszul complex will be exact. Okay, so I hope that is clear. Please let me know if there is any doubt. We just wanted to check whether any non-zero non-unit, how, and what that set is, and we proved that it is exactly equal to this maximal ideal. So, and that's why we are done. Okay, great. So let us move to now this next question, that let M be a graded R module. Okay, and let this M dash or M1, whatever you want to call it, be this shifted degree term. Uh, I mean, we are shifting the degrees by A of this module such that A belongs to z greater than equal to 0. Then this Hilbert series of M dash, this new module with the shifted degrees or shifted grading, is this T power A H M R T. We have to check whether this is true or false. Okay, so this is the question, that when we shift a degree of a, I mean, in the graded module, when we do the shifting of the degrees, the the corresponding Hilbert series of this new module with shifted degree will have this form. Okay, so we have to prove this. But before we move, note that we already have this, right? For any module, this is, I mean, what we say. That's how the shifting is defined. I mean, this is defined, right? Defined in this way. So what is this M dash of J plus A? It is what? M dash of J plus A. It is M minus A, J plus A, right? So which is M of J plus A minus A. So which is just MJ. So now what I want to find is Hilbert series of this new module. So Hilbert series of M dash T over R is what? It is summation J in Z rank of mj. I mean, this is the definition of my, what I can say, or this is the definition of Hilbert series. But instead of j, I can just, I mean, what I can say, change the variable thing. I can change the variable. Instead of j, I can take j plus a in z, and nothing will change much. J plus a dash t power j. So far this is okay. We are just changing the variable. So here j plus a in z, rank of, but note that this m dash j plus a is just mj. So rank of mj, oh, here also it must be j power j plus a, here t power j plus a. Okay, I mean, we are just using this m dash j plus a. Okay, we are using this here. Let me just highlight this. So now here, this is the rank of mj, t power j plus a. So a is just some, so I can write this, I can take a common. And here also I can just shift this. I mean, this doesn't change. Rank of mj, t power j, t power a. Or let me just write this carefully. J belongs to a, t power j plus a, which is summation j in z, t power a, the rank of mj, t power j. A is not, I mean, disturbed by this thing. And I can take t power a common because a is fixed. And now it becomes j plus a belongs to z. And I mean, it is just like we are, I mean, j belongs to z is j plus a belongs to z, right? So the summation the summation is running over all the integers in short. And we get this. And this is nothing but just t power a h m r t. And that's what we wanted to show. Is this okay? We got this. We started. I mean, we had to just observe this first part, and we got this t power a into. By definition, this is the Hilbert series of M. Okay, great. Let us move to next question. Question 6, I guess. Yeah. So now this question is also related to Hilbert series. So let R be K, W, X, Y, Z. And then does there exist a finitely generated graded, okay, this graded R module M such that HMT is equal to T cube divided by this 1 minus T square. Okay, and we have to use this. No, so we have to find a graded module M such that I have this. So note that uh, so, so note that first thing, that HR of R, so a module R over itself is this 1 minus T power 4. Okay, I hope this is clear because this is from this fact. So let us see how this comes actually. So if R is n graded, and so R naught is just my k, and R is my this kx1 to xn, and M is z graded, finitely generated R module. So M is n graded and R is n graded. Then M is this summation mj, j in z, And this becomes my Hilbert function. Hj, this is my Hilbert function. And by definition, we have this, right? HMRT. It's just summation j in R, rank of mj, p power j. This is what we have. Okay, so in case of Rx1, Rxn is what? R0 plus this x1 R plus this x1 square R, so on, right? So each I degree module. So this is degree 0, this is degree 1, this is degree 2. And these are the only, it is generated by only one element. So this Hilbert function becomes 1 for all j, because each degree component is generated by only one module, one element over R. Okay. So therefore, this HR T is summation p power j. J belongs to z greater than equal to 0, which is 1 plus t square and so on, which is 1 by 1 minus t. Is it okay? Wait, it must be k here actually. It's k. But that's okay. Not that doesn't really make any much difference. But I hope this is okay. So now in case of two variables, if I take R to be x1 comma x2, that R as R module, or then R is R0 plus, it is still R over R module, but we check dimensions over field. So it's generated by this x square comma xy comma y square R plus and so on. And again here h0 is 1, h1 is 2, h2 is 3. So Hilbert function becomes j plus I for all j. This is my Hilbert function. So this Hilbert series of kx comma y, or let us write me r rt, it's just this 1 plus 2t plus 3t square and so on. And this actually has this expression 1 minus t whole square. You can check this. This is arithmetic geometric progression. The coefficients are in arithmetic progression, and the variables are in geometric progression and so on. So we can have this, and in general, if R is this k x1 to xn, and R as a, again we are considering R over itself, then this RD, which is homogeneous degree D component, is generated by this, right? X power, x1 power, it is just this n plus D minus 1 and minus 1. Okay, because it is generated by what? X power A1, x1 power A1, x1 power A2, xn power an, such that summation ai from 1 to n is D. Okay, and this A1 to AI has this many choices. N plus t minus 1, choose n minus 1. Okay, and then this Hilbert series become d greater than equal to 0, n plus d minus 1, n minus 1, t power d. And you can check this. This is nothing but expression of 1 minus t power n. Okay, so in general, this Hilbert series has this expression. So in our case, we have HRR t is 1 minus t power t, not this, t power n. I hope I didn't make, yeah, this much is, yeah. T power 4 since R is k, W, X, Y, Z. Okay, and now I want to deduce from this. So required expression is, I mean, we want M such that HMRT is t cube by 1 minus t square. 1 minus t square. And we have used this result even in the last lecture. We will see, I mean, a quick proof of that result in maybe tomorrow's, just a second. Yeah, in tomorrow's lecture. But for now, again, we will use the result which we used last time, that let F1 to Fm be a regular sequence. Yeah, F1 to Fm be a regular sequence of homogeneous, again, polynomials in K x1 to xn. Then H R mod F1 to Fm. T is product of 1 minus t power degree Fi. When we used this last time, product divided by 1 minus t power n. Okay, the n variables. So we have this. So if I want to go from this t power 4 to t power 2 here, what I want to do, and here it is 1 minus t degree Fi. So if I do, I mean, if I am able to do this to my obtain, I mean, this expression here, then at least I will get this denominator as 1 minus t whole square. So what I want to choose is, I want 1 minus t. So it is t power 1. So I want to choose a regular sequence of two elements where both of them are from degree 1 component of my ring R. So let us choose, so want to do, so which is this. So choose I is equal to W comma X. It is a regular sequence, right? I mean, so I get this H R mod I R of t becomes this 1 minus t into 1 minus t divided by 1 minus t power 4. Number of variables is 4 here. So which becomes 1 minus t square. So this is regular sequence. And now what I want, t cube. So note that in previous question here, that is, if I shift the grading by 3 in my obtained R mod I, then it will be t cube and whatever we have for R mod I, right? And it will definitely, and it will exactly the expression which we want here, t cube divided by 1 minus t whole square. Okay, so the required module M, therefore so if we choose M, so if we set N to be, or let me write M to be R mod I, then M dash, which is M minus 3, will have Hilbert series t cube by 1 minus t square using question 5, I guess. Yes. So and this is free module because I is generated by two variables. It is free over R. R is free module over itself. So R quotiented by is again a free module. And we are just shifting a degree. So that doesn't change the freeness of our given module, which is R mod I. So this is free module. And we actually have this module M, which is R quotiented by I with the shifted degree 3, which gives me Hilbert series to be t cube 1 minus t square. Okay, which is my t cube. This was actually t cube Hilbert series of R mod I R t. Okay, and this actually gives me this. Is this okay? Okay. So question 6 now. I'm sorry, question 7. Let R be kx x. This is kx quotiented by x here. And now consider the R module map P from RE3 to RE4. Sorry. R direct sum RE4 going to RE1 direct sum RE2. Okay, and such that E3 is going to x square E1 and E4 is going to this x E1 plus x square E2. And what we have to check is, we have to check whether true or false that the annihilator of the image of E2 in co-kernel of phi, co-kernel of this map phi is, or phi, is x square or not. Okay, so I hope you know what is co-kernel. So co-kernel of phi is what? Image of this map, sorry, this R E1, R E2, which is my codomain, divided by this image of map phi. That is co-kernel. And what we want to check is annihilator of image of E2 in co-kernel of phi. So what we have so far here is this map. I have this RE3 plus RE4 going to RE1 plus RE2, right? This is my map P. Okay, and now I have again this map RE1 plus RE2 quotiented by this image of phi, right? This is nothing but my co-kernel of phi. So this E2, we have to check the E2 in co-kernel. Image of E2 in co-kernel means this E2 is going to E2 bar here under co-kernel. So now I want to find what is the annihilator of this E2 in the image of co-kernel. It means that this is module map. This is R module map. These are all R module maps. Okay. And these are all R module maps. So when I say this, what exactly I mean is I want to find all. So E goes to E bar. So I want to find all the X in R such that X E2 goes to 0 bar here actually. That's my annihilator. I mean, what annihilator, what I was saying. Those are the annihilators of this element. And I need to check that whether X square, the ideal generated by X square in R, whether that generate my annihilator of this element E2 in co-kernel of P. That's what I need to check. Okay, so since I need to check for X square, so suppose X square belongs to this annihilator of E2, right? So under this map, what it means? That X square into E2 bar, okay, E2 bar, right? Annihilator of image of E2 in co-kernel. So E2 bar is 0. That's the definition of annihilator. So this imply what? That X square dot E2 belongs to image of P, right? What is something belongs to 0 here in co-kernel? It means it belongs to this image phi, right? Either it's 0 or it belongs to the image phi. So it belongs to image phi. So once something is in image phi, it means what? It it is some A E4 plus B E3 in this module. So this implies that there exists A comma B in R such that A E4 plus B E3 is equal to X square E2, right? Oh, no, sorry. Phi of this thing is X square E2. So these imply what? Since this is phi E4, this R module map. So A and B comes out, and phi, this is phi which I'm using, E3, which is equal to X square E2. And what is image of E4? It is X E1 X square, and the other one was just X square E1. So it is A into X E1 plus X square E2 plus B X square E1, which is equal to X square E2. And if I just take all the coefficients of A and E1 and E2 together, it becomes Ax square Bx square E1 plus X square E2, which is equal to X square E2. So these imply what? My A, so this becomes Ax plus Bx square E1 is equal to 0. Oh, oops, here B. So if I compare both the sides, then Ax plus Bx square. So this is what? 0 dot E1 plus X square E2. So this becomes Ax plus B1 square is 0 and B is 1, right? Because I get Bx square is equal to X square. These imply B is 1. So these imply Ax square plus X square is equal to Ax plus X square is 0. These imply X into A plus X. Is there any error? Yeah. Yes, Ax plus Bx square is equal to 0. So this imply Ax is equal to X square. Is this okay? Ma'am, ax square e2. Yes, yes. So this implies a is equal to 1. That is correct. That is there any error? But the moment I have a is equal to 1, this implies ax plus bx square is equal to, sorry, x plus bx square is equal to 0. So this implies that x into 1 plus, let us just manipulate this. This implies that bx is equal to 1. Wait, just a second. So bx becomes minus 1 then. But b is anyway 1. So this implies x is minus 1, which is unit. But that's, so this implies x is unit in R. But that is contradiction, right? Because R is what? It is kx localized at x. So all the elements which we are inverting are outside x. But this x belongs to this ideal generated by x, and this is unit. So which is contradiction. So yes, A and B both we were getting 1, but they both of them becoming 1 is actually giving us a contradiction by getting that x is a unit. So which is contradiction, because this and this is also maximal ideal in my ring R. So x is a unit which belongs to maximal ideal. So that is definitely a contradiction. So no such a comma b exist, okay? Because if they exist, then we get x belong to units of this local ring are localized at ideal generated by x. So therefore, this, what was the question? Therefore, x square does not belongs to any letter of E2 bar. Okay, so therefore, any letter of E2 bar is definitely not equal to an ideal generated by x square. I mean, forget about the ideal generated by x square. The x square itself, the generating element of this ideal which we are considering here, it itself is not annihilator of E2 in the image of co-kernel of P. Is that okay? Where it is ax plus, okay, here it should be ax square. Okay, this was supposed to be a here. This is b. Okay, okay, I got it, what you mean. So ax square is equal to x square. So a is 1. And once I have a is equal to 1, a plus bx square. Okay, so this was the error you are saying. While collecting, it should be bx square and ax square e2. I think that's what you were. Yeah. So let us check what contradiction we get in this case. So again, x we can cancel out and get 1 plus bx is equal to 0. So bx is equal to minus 1. So once I have bx is equal to minus 1, This again implies that X is a unit. So we don't need this. I mean, we don't need this actually. Don't need this. And again, it becomes, so this implies that X is a unit in R, right? Because X into something is giving me -1. So this implies X is a unit. So anyway, we got the contradiction which we needed, that X still becomes a unit. Bx becomes -1, then X becomes a unit. And yes, is this okay now? A is equal to 1 implies. So we still, so Bx becomes -1. So X still becomes unit because, yeah, I mean, X becomes unit, and again, X is in maximal ideal. So X cannot be unit, and no such AB must exist then in that case. And therefore, X square is not an annihilator, and that's why it can't be ideal generated by X square. So you said Betti number, right? So let us do one example of Betti number, which you were asking. We will do the same. Okay, let us do this. This is question 8. Just a second. Yeah, let us do this. The Betti number. Question. Oh, question 8. That let R is equal to K, X, Y, Z, and I is this ideal X, Y. I mean, I'm just using the example from last week. So what is graded Betti number? Beta 2, 4 R mod I. This is the question. Okay. And so what is Betti number? First, let me quickly. So this is definition plus proposition, whatever you want to call. So let M be finitely generated R module. Let us quickly go to the definition. Then M has a graded minimal free resolution. I hope you know what is minimal free resolution. Okay. That is complex. That is this complex. F2 going to F1. Of finitely generated graded free modules Fi with degree preserving maps. So note that earlier when we calculate the minimal presentation or CGGs of this resolution, what we actually got was, I mean, if you remember, we had this kind of, F0 and then F1 and then kernel of this D1. And since kernel will again be a free module, I will have this F2 R module such that this is again a surjective map from here to here. And again, we check the kernel of that map and so on, and we continue. And what we get are CGGs or the minimal presentation matrices. Okay. And we want those to be degree preserving maps. In that case, we call it a minimal free resolution. And the graded Betti number are this beta ij M. So since this free resolution is of M, it is number of copies of R minus J in Fi. So in order to have this Fi to Fi minus 1, a degree preserving map, we can shift the degree. For example, if I have this map, x going to x square. Okay, so every degree 1 term is going to degree 2 term. But I want it to be degree preserving map. So what I do, I shift the degrees by 1. Okay, so if I take, so this degree 1 component, so this is my R1, right? If I make shift the degree such that this becomes R2, it means what? I shift it by minus 1. Then my degree 1 component, which is my R2, is going to now R2 here. Oops, I want to make this R1. Yeah. Now these two. So this minus 1 or 1, whatever. So this 2 degree component, I want to send it to 1 in short. So this 1 minus 1, so this is R2 I need. So this is, I want here A such that A plus. So what we have, M A J M I J is M I plus J, right? So I want this to be R2. So degree here I want something such that, so, but it is R1. So I need to have minus 1 here. So minus 1. So R minus 1, 2 is now going to R2. So now it is degree preserving map. This is shifted degree by minus 1. But now the 2 degree component is going to 2 degree component here. Is this okay? Because this is R minus 1 plus 2. This is R1, which is this X. And now it is going to X2, X square. So this shifting of degrees is what we do when we want to make this map Fi to Fi minus 1 a degree preserving map. And in that case, this number of copies of Rj. So for example, the map could be of like this, y going to y cube, for example. Then instead of this minus 1, I will have to make it minus 2 or something like that. And then these copies, I mean, there are different degree copies will be available in my free module F. Okay, and we have to count the number of copies of this R minus J. So let us understand this by example. So this number of copies in minimal free resolution, okay? And minimal free resolution is, I mean, in that we need to have degree preserving maps. So for example, which we had this last time, right? R going to 0, and here it is R is what? Xy, y square, xz. So it was R3, right? This epsilon map. And here it is, if you remember, it was this minus y x0 minus z0y. This is E1 going to xy, E2 going to y square, E3 going to xz. If you remember, this was the given condition. And these are the, what I can say, minimal presentation, or these were the CGGs which we had. And this is now again a free module, right? And I have these 2 elements here. What are these 2 elements? The 2 elements here are, so kernel of this epsilon to this, I have inclusion, and kernel of this epsilon is generated by this ye3 minus ze1, comma, xe2, comma, minus ye1. This is what my kernel is generated of. But now note that even need to have a degree so that this becomes a degree preserving map, right? Even, so what I do, I assign degree of even to be 2. Okay, so each of this, so assign degree of even to be 2. So it is, so I'm assigning degree to be 2. And now again, I want to find CGGs of, so this is from R2 to here now. So this is R module generated by 2 elements, this one, this first element and this second element. So I will again have this R2 to R3 map. But can I have CGG among this? Can I find a zero set of this? So what is this? This is -y. Consider this as this tuples minus z0y. Can I have a R linear combination of these two elements such that I get 0? Some alpha plus beta of these two such that I get 0, 0, 0. Is this possible? 0, 0, 0 or just 0 doesn't matter. Or let me write this. Can we have this? No, right? Because whatever I multiply here, the second term always remains 0. And here also, this third term always remains 0. And y, if I multiply, and this x and y are non-zero divisors in my ring R, X, Y, Z. So this is just injective math here from this R2 to R3. But for this element to make, so this EI is of degree 2 and YE3 is of degree 3. So this map here, to make it degree preserving map, what I want to, I will assign degree of this, if I consider this R2, right? So F1 going to this first element and F2 going to this second element. Let me just shift it here. So this F1, F2, I need to assign some degree and assign it to be 3. Do you understand what I'm doing? So here x1, x2, degree 2 term. So what, and this R is just a copy of R, but I want it to be degree preserving map. So I shift it by -2. Okay, so -2, 0 element goes to this xy, which is degree 2 term. Okay, similarly, so yeah, similarly here, these are degree 3 elements. This kernel epsilon is generated by this degree 3 element. E3 has degree 2, Y has degree 1, so Y E3 becomes degree 3 elements. So I assigned here the degree to be -3 so that it goes inside degree 3 terms. So R0 here, that is constant. 1 will go to where? XY, right? Multiplication by XY. 1 into E1 goes to XY. So 0 degree term is going to 2 degree term. So it has to be R minus 2, 0 and so on. So CGG is what? So now CGG is, okay, it will take some time, but I want to finish this. FM in R. Here F3 is 0, okay? This is my F0, F1, F2, and this is my F3, which is 0. FR is, R is K x1 to xn, graded homogeneous. And CGG of F1 to FM, I mean, we did this, is an R linear combination, summation Ri Fi is equal to 0. And in this, we have made observation that if Di is degree of Fi, then this summation I from 1 to m R minus DI to I such that EI going to FI is degree preserving map. Okay, so that's what we are doing here. So this is degree of I is generated by 2. So F1, F2, F3 if I call them F1 or yes, F1, F2, F3. So E1, E2, E3 has to have degree minus 2. So what I have here are going to 0. But now using this, I have this R minus 2 I from 1 to M, 1 to 3. Okay. But now my minus R3 is going to degree 0 element. This is F1 is going to degree 3 element here. So this has to be R2, which is summation R minus 3 I from 1 to 2. This is 0. I hope you understand here. This I is, and I am multiplying it by Fi. So my CGG here, so this Yi's are, I mean, you will get. So when I say this beta 4 I, so this is my F0, F1, F2, F3, and there is no F4. So beta, what is it? Beta I comma j is minus j degree copy in Fi. So this is minus 4 degree copy in F2. But F2 does not have any minus 4 degree copy. So it is just 0. Is this okay? Please understand how we are assigning the degrees here. It has to have a degree preserving map. E2 had degree 2, but this kernel epsilon, I want this map to be degree preserving map. So I need to have, so here it is R minus 3 and multiplication by 2 will give me a degree 0 element and so on. And this Betti numbers also can be calculated in Macaulay 2. But in Macaulay 2, let me show it to you, like how it is done in Macaulay 2. So let me clear all. If you have any doubt, please ask me. But I will show you how this Betti number is calculated in. Okay, so my R is, let me stop here so that you can see this. So my R is what? Q, X, Y, Z, yeah. Q, X, comma, Y, comma, Z. And I is this ideal, I. Oops, ideal, X, Y square, X star Z, yes. Then Betti I is this. Sorry, not Betti I. I need to find C is equal to resolution. Betti element of resolution of M. So resolution of this I and now Betti of this C. Okay, so now it is the complete. So when I say Betti I, what it does is it only considered this first map, the epsilon map which we had in our notes, and it just calculate the Betti numbers of that first map. I mean Betti numbers for that first graded map. But Betti C, so it is like the entire resolution, and it gives the information about information of all the Betti elements. But the trick here is when we have this kind of structure in Macaulay 2, it is Let me share my screen again. So here in this screen where I have written, this is beta 24. But in Macaulay 2, when I write this beta 24, it is actually the, we can see from the Macaulay 2 screen here that it is 0, 1, 0, 1, 2, 1, 3, 2. This is total Betti number, and 0, 1, 1 dot dot 3, 2. So this is the expression which we have, and it means it is. So if I look at it as table, so the gamma ik is actually beta I comma I plus k. So what I want to find is beta 2 comma 4. So it is beta 2 comma 2 plus 2, right? So it is gamma 2 comma 2. So second row, second column. But from this Betti table which we have, Betti of C, which I have here, there is no second row, right? There is no second row in this Betti tally. So this is just 0, which is what we are getting anyway, the Betti element in the resolution. I hope you can see both this, this screen, which I'm showing here. Okay, and in to check everything in details, what we can do is this C is a complex. So this C dot dd actually gives information about all the degree terms. So this is degree, this is first, this is second, and this is third. What I can say, third, three F1, F2, F3s, and F0, F1, F2. This is degree 2 terms, all these degree 2 terms here. And this is my third map. Is this okay? So this is map of degree 1, this is map of degree 2, this is map of degree 3. So this R2, we need to assign a degree 3. And if I want to calculate beta, let me show this. If, okay, good. So this beta, if I want to calculate degree 3 term, beta 2 comma 3, then it is beta 2 comma 2 plus 1. So it is gamma 2 comma 1, right? So second row, first column. So in Macaulay 2, the counting start from 0. So 0, 1, 2. So second row, first column. So 0 and then first column. So this is 3. So there are 0, 1, 2. So it is 2 copies of 3 degree terms. Okay, so this is 2, 1, which we are calculating. And there are 2 copies. In F2, there are 2 copies of degree 3 and so on. So I hope this is clear, and you can check different, what I can say, ideals, and see what you get as you keep on calculating this Betti numbers and so on. So this was the I hope this is clear, and how to calculate everything and how to see the degrees. Okay, if there is any other doubt, please let me know. I think gamma. Okay. So this Betti table has this gamma value means I'm considering this table to be gamma. Okay. And if I want to find, if I consider the ith entry in gamma, then this entry here, ith entry, actually expresses this Betti number of I comma I plus k. Okay. So this 3 here, which is what? This is gamma 1, 1 is what? 1 comma 2. This 3 here, it is gamma 1 comma 2. It means in F1, there are how many degree 3 terms? Degree 2 terms. So F1, which is this, how many degree minus 2 components are there? It's 3, right? So that's what we are getting here. Gamma of 1, 1, which is beta 1 comma 2, which is 3. That is beta 1 comma 2 is number of copies of R minus 2 in F1, which is 3, right? That's what we have here. That's what this gamma does. So gamma is just, I'm denoting this table. And so here, this is 2. So what this 2 imply? This is gamma 1, 2, right? So which is beta 1 comma 3. Sorry, I think I need to consider B, 2 comma 3, 2 comma 1. So this is 2 comma 3. So in F2, the degree 3 terms. Ith entry, when I say this I is number of Fi and k is number of row actually. Number of, yeah. So this is beta 2, 3. So in F2, the number of 3 degree component, that is 2 here. So I hope this is clear. When I take Ik, I actually are like considering ith column, kth row, and so on. So which is 2 here. So gamma is just a name. I mean, just to locate the entry in this Betti table. So I hope this is clear now, the Betti numbers and how it is calculated. And is this okay? Yes, gamma 2, 1 is beta 2, 3. Gamma I comma k is beta I comma I plus k. So as you ask, gamma 2, 1 is beta 2 comma 2, 2 comma 3. Just follow this notation here, and I will highlight also. It will be easy to understand. And this, okay, so, and yeah, I hope this is okay now. If there is any doubt, please let me know. Otherwise, we are anyway over 5, so we can end the session now. Is this okay? Do you have any doubt? Okay, no doubt. Okay. So we will meet again tomorrow. And maybe I will try to do the Betti calculation for the question which you asked. Okay, and not this ideal. If okay, then I think we will end this session now. Thank you. See you tomorrow. Bye.